I'm about halfway through going through the worksheets. This class is done, but I'm gonna wait till I'm done all of them before I post the marks. I mean, it should have simply been repetition. And for the most part, people were doing what they should have. But it always surprises me how specific I can be on the board and how somehow in the space between the board and some students' eyes or hands or minds, that what I put on the board doesn't translate at all to what ends up on the worksheet, which is interesting to me. But be that as it may. What I want to start with today is something that I said I'd do last time we met, and that's activity 3.3. So we're not using a beaker and water, I'm using a petri dish. And the point behind the petri dish is I want to maximize the surface area of the water in contact with the air, so that liquid surface area, as it increases, so will the evaporation of it. So here's my scale. And if you look at the instructions, this is page 123. Evaporation occurs when a molecule on the surface of a liquid is struck with enough force by neighboring molecules to break away from its attractions to those around it. What would be striking that? Those would be gas molecules from the atmosphere. So 79% of the air we breathe is nitrogen, about 21% is oxygen. Those molecules are moving very fast. They are going to be colliding with all the water molecules on the surface of that water, giving them sufficient energy to leave the surface of the water and enter the vapor phase, and that's evaporation. Evaporation is often depicted like popcorn being popped, and then he has to put all that in there. Let's use the mole concept to calculate the actual rate at which water molecules evaporate. And we're going to do that. What we're going to end up with eventually is molecules per second. Okay? So I'm going to turn the scale on. Now, as you're going to see, the mass difference after 30 minutes is not going to be dramatic in terms of grams, but it will be dramatic as when we do the arithmetic to do molecules per second. The water has to stay in the petri dish, otherwise this is a waste of time. Yeah, a little more than that. So 104.08. Stopwatch, and 30 minutes, and it's done. And we'll measure it again. We're not going to chart it minute by minute because the change is too small, but if you look at what's in the table, we end up having, the time of day doesn't matter, we're just going to go by the stopwatch, okay? So mass of beaker in water, 104.08 grams, and then the final mass, the difference will have to be the amount of water that's evaporated. Calculate the number of water molecules evaporated during the trial. Now, how would we do that? Well, we've got grams of water. We're gonna convert that to moles of water. And using the molar mass of water, which is in using the information in the periodic table in our book to 2 decimal places, 18.01 grams per mole. Once we have a number of moles, we're gonna get molecules. So it really is just a 2-step event here. So we're gonna go grams to moles, moles to number of molecules. Now that number of molecules would have left the surface in 30 minutes, which will convert to seconds, and we'll get molecules per second. Okay? And Gary makes it pretty clear that you might be surprised, although the mass in macroscopic terms is rather small, the molecules aren't. Okay? I asked you to look at several questions in the 3.3 review, and as usual, check all of your answers each time. Were there any that gave any of you trouble? Meaning, after doing them and checking your work, you didn't get the right answer? Yep.
It's not like, the question, not one of the questions, but like, is there a way to write molecules shorter?
You know, like the word's too long?
Sometimes it like takes up space, so is there like a shortened version for it or not?
To use more space. Like there's not enough space in the book, I will grant you that. And that's Lionel trying to save pages so that the cost of the book isn't so much. But I would, if it means you have to do it on a separate sheet of paper, do it on a separate sheet of paper. I mean, you're not gonna be writing tests on this material where I give you that much to do, I give you that much to do. So if you need extra work, just write extra work, but there's no abbreviation that I use for number of molecule. Which reminds me, some of you on your worksheet decided no matter what, you weren't gonna use extra sheets of paper. So the writing that's on there is very difficult for me and you to read. And what some people did is, because there was so little room, they decided to leave units out or leave steps out. Some people decided for some reason they're gonna go to 1 decimal place with the mass values. I don't know why. But wherever it differed from what I asked you to do, I would make a notation on your worksheet, okay? Nothing in 3.3 that you think needs our attention? If all of you did the questions I asked you to do and you checked your answers and they were right, that's pretty good. That's good. That means we can legitimately move on. But as I'm saying this, if you're looking at a blank set of pages, then obviously you don't know if you don't know it. That's on you, that's not on me. So I asked you also to begin looking at 3.4. Now, 3.4 adds another thing along the rim here. And volume is actually going to be discussed in 2 contexts. One, volume of a pure substance, and then later on, volume of a solution. And then we're going to introduce something called molarity. Okay? If you had read the back side of the first page on your worksheet, you would have heard about one of the things Avogadro did to allow scientists to have confidence that when they're measuring gases, they have confidence that they're measuring the same number of the molecules. It's easy enough when you're talking about mass, you can measure on a scale. But for gases, for compounds and elements that exist as gases, how are you going to know when you're measuring the same number? Okay? Now that my computer's warmed up, let's begin page 126. All we're doing in the the first few pages of this section and the practice problems I asked you to do are taking care of a brand new conversion. And if that's here and this is here, that means we can get to it and from it to any other units on this wheel. That's kind of the whole point, okay? What's wrong with your computer? Okay. Just as the mass of a mole of substance called its molar mass, the volume of a mole is called its molar volume, which makes sense. The molar volume of a substance is the space occupied by a mole of its particles, whatever state they're in, okay? A solid's or liquid's molar volume is determined by the size and spacing of the particles, because effectively they're touching each other. We call these the condensed phases of matter. So obviously, because they're in contact with each other, the size that they are matters. Okay? The size of the particles has little effect on a gas's molar volume because the distance between the particles is so much greater than their size. So again, a simple analogy, let's say I had 100 grapes and 100 grapefruits. And I put 100 grapes in maybe a 2-liter beaker. That would be the space they occupy. They're all touching each other. If I took 100 grapefruits, I'd probably need several garbage cans. Obviously, the grapefruits are going to take up much more space because they're bigger. And if they're all touching each other, they're going to take up more volume. But if I took those 100 grapes and I spread them out evenly between the volume of BC Place, or the 100 grapefruits and spread them out evenly throughout the volume of BC Place, the volume that they occupied would have nothing to do with how big they are, because they're so far apart from each other. And because the space between the particles in the gaseous phase is so much more than the size of the particles themselves, that their size has nothing to do with the volume they occupy, because the vast majority of volume of a gas is empty space. Okay? Solids, liquid, and gases under constant pressure will expand when heated, whatever. So we can skip that paragraph. It's not true, it's just not important for here. Liquids and gases are more frequently measured by volume than by mass. A substance's molar volume allows you to convert the volume of a substance into its number of moles. And that makes sense. If it's moles per liter, liters per mole, then because you've got those two units in the conversion factor, going from one to the other would be equally straightforward. All of Dalton's evidence for the atomic theory came from combining mass ratios, and we went through that in the first section on relative mass. Okay? During the same time period when Dalton lived, other scientists were following a separate line of research, gathering data on combining volume ratios called volumetric data. So at the end of the 1700s, early 1800s, there was a lot of work and a lot of interest in hot air ballooning, particularly in France. The French chemist Joseph Gay-Lussac found that gases measured at the same temperature and pressure when they reacted with each other, always reacted in whole number volume ratios. For example, 2 volumes of hydrogen gas and 1 volume of oxygen gas is always what reacted together to produce 2 volumes of water vapor. And it was an interesting observation as far as he was concerned, but it wasn't until Amadeo Avogadro looked at that he made the connection between the volumes and the number of particles. Using Gay-Lussac's findings, the Italian chemist Amadeo Avogadro hypothesized that the reason the gases were reacting in integral volume ratios was because at the same temperature and pressure, those volumes contained the same number of molecules. And that's a very famous hypothesis. Avogadro hypothesized that equal volumes of different gases measured at the same temperature and pressure contain equal numbers of particles. Modern chemists still refer to this as Avogadro's hypothesis. And what it allows us to do is have confidence in that we're measuring the same number of gas molecules. All we have to do is make sure they're in the same size container at the same temperature and pressure. And that's how we have confidence we're measuring the same big number. And remember, we don't need to know what that number is, if you harken back to section 3.1. All we need to know is that we're comparing the same numbers. And if we have confidence that we have the same numbers in those volumes at the same temperature and pressure, then the mass ratios of those volumes should be the mass ratios of individual molecules, by exactly the same reasoning we used when we were talking about solids. Okay? Let me just check this. We're not at 30 minutes yet, but we're not even at 15 minutes yet. Now, if equal volumes of gases at the same temperature and pressure have the same number of gas molecules in them, and it only applies to gases, okay? Then what volume at an agreed upon temperature and pressure, what volume would contain a mole of a gas? And as long as chemists agreed on what that set of volume and pressure conditions were, then they would know that any time they had that volume at the agreed upon temperature and pressure, they would have a mole of gas molecules. Chemists have agreed on that, and they refer to it as standard temperature and pressure, STP for short. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere pressure, the pressure at sea level, 101.3 kilopascal. And as long as any gas is at that temperature and pressure, then a mole of its particles will occupy 22.4 liters, okay? So anytime you see the letters STP, write that down, because it's referring to gases, and it's telling you that a mole of the gas you're dealing with will live in that volume. How big is 22.4 liters? I'm glad you asked. See that box? That's 22.4 liters. Give me a second.
I'm so glad you asked. Well, how much is 22.4 liters? I'm so glad you asked.
Why did he sound so happy about it? Damn, only 20 minutes into class, bro.
Hourly only
The
20 minutes.
equation that you're looking there is called the ideal gas equation. PV equals nRT. whole bunch of stuff on this box, okay? Well, let's leave that for now, okay? So that's 22.4 liters. There was a lowercase l there, so I changed it to a capital L. As long as you're at standard temperature and pressure, 0 degrees Celsius, 1 atmosphere, any gas, regardless of how big the molecules are, regardless of how heavy the molecules are, will have a mole at 22.4 liters, okay? Now, obviously, if we're not at 0 degrees Celsius or 1 atmosphere pressure, that doesn't hold. And you say, why did they pick 0 degrees Celsius? Well, they could have picked anything as long as they agree on what the S means, the standard means. Now, let's say you did it at regular room temperature, say 25 degrees. Well, they also have a number for that. So if it's standard atmospheric temperature and pressure, affectionately known as SATP, which we're probably not going to worry too much about, rather than 22.4 is 24.5. But from now on, when you see those letters, somewhere write 22.4 liters per mole, because it means you're going to use it. That's the only reason you would see these letters, okay? And what it does for a gas instantly is allow us to go from liters to moles, okay? As long as we're at STP, okay? Well, all gases at the same temperature and pressure have approximately the same molar volume. Each solid and liquid has its own characteristic molar volume because the molecules are touching each other. You may not think you do, but you can calculate the molar volume of water. What's the density of water? One what? Density is mass per unit volume. What's the mass of 1 milliliter of water? You guys need to connect a few dots here from previous classes, you guys. Don't start every day as if you haven't been here ever. 1 gram per milliliter. 1.0 gram per milliliter. You did a worksheet on it. Remember that hyperbola? Remember the mass of volume at 4 degrees Celsius? The density of water? 1.0 grams per milliliter. Slope of the line. Remember that? It was a long time ago. You were younger. It was in September. But, okay? Now, how does that help us get the molar volume? Well, we know grams per milliliter, which you could also write as milliliters per gram, couldn't you? So what are the units of molar volume? Liters per mole. With a gas at STP, that's it. But what about a liquid? Okay. Water's density is 1.0 grams per milliliter, right? If you have milliliters, you have liters, right? Can't you convert grams to moles? Let's say that we converted that to liters. You would agree a milliliter is a thousandth of a liter, right? You want to get moles in the bottom, we want grams to cancel. Don't we just multiply that by the molar mass? Doesn't that have to equal liters per mole? Point 001 liters. What is that?
No way. No shot. 16. That was 15.
How many liters per mole? Just divide that by 1,000, you guys, for God's sake. Louder?
0.012.
0.012?
0.012. 01, but I'm providing two zeros.
Well, if you want to, I mean, I got 4 sig figs here, so isn't it, you sure it's .012?
1.8.
Yeah, 0.018, isn't it?
Or I read the 8 as a 2. That's
Now, if it's 0.018 liters per mole, it's also 18 milliliters per mole, right? I mean, if you left it as milliliters, you'd have milliliters per mole. So if I measure 18 milliliters of water, I have a mole of water. I have 18 grams. And if I can say that in 18 milliliters, I have a mole of water, I can also say that in 18 milliliters, I have 6.02 times 10 to the 23 molecules of water, can I? So what did I just do? Grams to moles to volume, volume to moles to gram. And it's interesting that I don't actually need to necessarily go through moles where it comes to density. And we'll talk about that later. In other words, there's a way around the side of the wheel, but we'll get there. Does that make sense? Okay. Now, that's not a gas, because the volume I have will dictate, obviously, the number of particles is gonna change the volume, given the fact that they're all touching each other. And that wouldn't be the molar volume, for example, of iron, or aluminum, or silver, or any other liquid, or any other solid. Because liquids or solids have different densities. And if they have different mass per unit volume, they have different moles per unit volume, okay? So, then we'll get there. Atmospheric nitrogen and oxygen react during lightning storms to produce nitrogen monoxide that is quickly converted to nitrogen dioxide. Now that's all interesting stuff, but that's not the question. This is the question. What is the volume of 1.3 moles of nitrogen dioxide at STP? Well, you see the letters STP. Somewhere you do like 22.4 moles per liter, because you know you're gonna need it. Now, if you wanna put the wheel up, you can, you don't necessarily have to, but remember, every wheel has the mole of that substance in the middle. So moles NO2 go here. Which of these two things do we start with? We start with moles and we get to liters. So here to here. But you can easily see that we didn't necessarily need to start with moles NO2. We could have started with grams NO2. Grams to moles to volume. So all we're doing here is that. Okay? That's the two. 600 liters of air at STP is compressed into a scuba tank. How many moles of air are in the tank? Well, you say, wait a minute, air is not just one compound. It's not just, or one element, it's not just oxygen, it's nitrogen and oxygen. But it doesn't matter. It doesn't matter what they are. The number of them is all that dictates the volume they'll occupy. So whatever molecule, whatever gas molecules there are in the air, that volume at STP can be converted to moles of air, moles of molecules in the air. I don't really like that question because he's kind of confusing the issue a bit, but I think the point he's making here is it doesn't matter what the gas is. As long as you know what the volume is and you're at STP, you can use that conversion, okay? Now, it's almost too obvious to concern ourselves with, but let's do one or two of these. The burn match odor of sulfur dioxide is often associated with pulp and paper mills. Cool, but the question is this. How many moles of SO2 are in 9.5 liters of SO2 at STP? So are we given volume or are we given moles? We're given volume and we're getting total. So we have to go here. But I'm gonna add something to it. How about how many grams of SO2 are in 9.5 liters of SO2 at STP? We draw the mole hill or the mole, the circle. Moles here. We're given volume, we want grams. Is that a step too far, you guys, or are you okay? Does that make sense? It's just a two-step conversion. Just like we did in the previous section, we're just adding a new unit. So how many grams of SO2 are in 9.5 liters of SO2 at STP? If we're not at STP, we can't do this, okay? And if you go back once again to the very first page of chapter 3. So page 101. You see the quantity on the left of the wheel, volume of the substance, 2 moles, molar volume, all right? Now, there are more mole volumes than associated with STP, but that's how you have to do that, okay? So, step 1, step 2, all we do is what we've been doing for literally months now. We're gonna go liters of SO2, because that's what we're given. We'll put the numbers in later. Liters of SO2, moles of SO2. And once we're here, we can get anywhere. We could answer how many molecules of SO2 are there. We're asked for grams. Liters of SO2 goes here. Moles SO2 goes here. You saw the letters STP in the question, so you wrote that down. But notice it's not 22.4 moles per liter. It's 22.4 liters per mole. All of the molar conversions we've talked about so far have 1 in front of moles. Grams per 1 mole. Liters per 1 mole. So make sure you don't get the 22.4 in the wrong place. That's what I mean when I say let the units guide you, okay? And this is just all notes. Sulfur is 32.07. So 32.07 plus 32.00. And if I was giving you this in a question, I wouldn't need to see in 1 mole of SO2. 1 mole of sulfur, 2 moles of oxygen. 64.07 grams. I would just need to see that. Okay? And what do we got for volume? 9.5. Okay, so that's not quite a half. You can estimate the 1.5. Because this is 3 sig figs, that's 4, that's 2, your answer should have 2. Okay? And we could have also asked in the other direction, if I have this mass of SO2 at STP, what volume will it occupy? You must be getting close to 30 minutes now. And it doesn't matter what time it is, we'll make the correction. Okay, it's just 30 point 30.3. 37, and I hope this thing didn't turn itself off. If it turned itself off, we gotta start over again. Actually, it's okay. Yeah, you know what? It turned itself off for some reason. That's ridiculous. Huh, now it's on. Well, I'll just start from scratch. It's okay. I'll just measure the mass. Let's go 98.2. Now that was, I believe, more like 31 minutes, 30 seconds. So let's do the arithmetic on that. So we get 7 here, we get 7 there, we get 5 there. And we should be done 5.77. Can you guys work that out? So how will you calculate the number of water molecules evaporated during the trial? And what do we have? You can use the wheel model. So we've got 5.77. Let's use the wheel. In case you guys are wondering how to do this. You know how to do it, you just haven't been asked to apply it. So, wheel, moles of water. That's grams of water, okay? So we go moles, moles. Now, that mass of water was 31 minutes and 30 seconds. So, let's go. We have grams of water per minute. 31.5 minutes, correct? Okay. And we've got 5.77. Now, we don't want grams per minute, we want molecules per second, right? So we've got to take care of the top and the bottom. Remember we were doing that way back in chapter 1 that Sherry wrote? So let's just use the arrows. We're going to go grams, moles. Let me take care of the top first. We're going to go moles, molecules. And then we're going to go minutes to seconds. Does that look familiar to stuff we were doing way back in September? Grams goes here. Moles goes here. Minutes goes here. .01 grams per mole. 6.02 times 10 to the 23 molecules per mole. And 1 minute. Let's go through some things there, 60 seconds. Actually, this is a definition, so we don't need to worry about stuff right there. You can keep 360. So what do you get I think Gary asked it stepwise, but I figured let's just do it this way. So how many molecules do you get per second? It's not a big mass. How many molecules do you get per second? Big number? How big? Anybody? No, it's not a test, I just, how big is the number? Say it loud.
1.02 times 10 to the power of 1 square.
10 to the
Power of 20.
per second. Not for the entire 30 minutes, per second. Anything times 10 to the 20. That's 100 million trillion molecules per second. Look at that. Not a huge mass, but again, there's evidence that molecules are unimaginably small. Okay? It's not a test question, it's just, as Gary puts it at the very bottom, be suitably amazed. Oh, come on, more amazed than that. I don't know if it's gonna keep you up at night, but again, it's how useful the mole can be for us. Okay? Now notice number 3, the difference between number 2 and number 3 is you don't see the letters STP, do you? Because it's not a gas. Silicon dioxide, better known as quartz, has a molar volume of that. What is the volume of 0.39 moles? Well, there's the conversion between the volume and the moles. And why aren't we using liters? Usually it's because solids, we use cubic centimeters or centimeters cubed. This doesn't really fit in with our STP, but it is a molar volume. And he hasn't referenced the temperature there, but temperature would probably be somewhat of an issue, not pressure because it's a solid. But again, it's just moles to centimeters cubed. Now this is what we just did on the board. Volume to moles to mass, volume to moles to number of items. So for SO2, we could have said in number 2, how many molecules of SO2 are in 9.5 liters of SO2 and STP? Liters to moles to molecules, liters to moles to grams. It's not really any extra chemistry, it's just an extra step. Okay? So we could have done this to this. We did this, but we could have gone that way. And if we can get from here to here to here, or here to here to here, we can also get from here to there, or there to there. We've already done this. We've already done that. We're just adding another thing on the rim here. So given any mass of SO2 or any gas in STP, we can find out what volume it'll occupy. Given any number of moles of gases at STP. We already know how to find out the mass of that, but we could also, what volume would they occupy? And there are 2 sample problems here, none of which are really beyond what you guys are able to do. The gas in neon signs is at extremely low pressure. How many neon atoms are present in the sign containing 75 milliliters of neon gas? Well, it's not at STP, okay? At a molar volume that is 100 times greater than the molar volume at STP. Obviously, if the pressure goes down, the volume's gonna go up, right? So if you've got a really low pressure, you've got a really big volume. You don't need to worry about this graph, but something courtesy of Robert Boyle, Boyle's law. The gas, volume and pressure are inversely related. As the pressure goes down, the volume goes up. As the volume goes down, the pressure goes up. It doesn't matter what you put where, okay? You get that, okay? So if the pressure is really low, the volume's gonna be high. And the volume, he said, is 100 times greater than STP. So if 22.4 liters per mole is STP, then 2200, 22.4 times 100, 2,240 liters per mole. Here's a mass question. Natural gas is used to heat homes and may fuel the Bunsen burners in your laboratory. Consists primarily of methane with a little bit of ethane. What is the mass of 8 liters of methane at STP? I don't think that any of you should have trouble with that based on the level of detail you've gone into. And I'm not saying you have to use the wheel. I'm just saying, at least at the beginning when you're doing these, it does help you. Just go about your sequence. So what chemical are we dealing with? We're dealing with methane. So moles, methane is here. And then we read the question again. What is the mass of 8 liters of methane, STP? So grams of methane goes there. We're given volume. We're also given STP, which means we write that somewhere. Step 1, step 2, just like we did with the SO2. 8 liters is a little more than a third of 22.4, so we're going to have a little more than a third of a mole. And if the molar mass is 16 grams, a little more than a third of 16, which 5.7. Okay, so that makes sense. And 2 sig figs here, 3 here, 3 there, and he's going to go to 1 decimal place in the mass, 5.7 grams of methane. All right? Or we could have said 5.7 grams of methane at STP would occupy what volume? 8 liters. Then we'd simply turn the arrows around. Nothing to it. Am I going too fast, you guys, or is this isn't that difficult, is it? I don't think so either. Now, this one's a little different, but it's not beyond what you guys have already done back in the last section. People often refer to the amount of carbon dioxide produced as the carbon footprint of a process. What volume of carbon dioxide at STP contains 20 grams of carbon? Now, do you see you got 2 chemical species there, carbon dioxide and carbon? See that? Now back when we were in the last section, this is a sample problem, agreed, but as you're analyzing it, if you've got 2 chemical species, you need 2 wheels. And at the center of each wheel is a mole of that substance. So let's do it from scratch, the way we did it back in the last section. And again, the only thing different here is we're adding another thing along the rim of the wheel. So we've got carbon dioxide, we've got carbon. So we want 2 wheels. So we start with information about carbon. So let's put moles carbon here. And we want to end with something about carbon dioxide. So we'll put moles carbon dioxide there. We notice that the letters STP are given, which means somewhere we write that because we're going to need it. We start with mass of carbon. We want to end up with volume of CO2. Okay? So, step one, that's molar mass, grams per mole. Step two, that's chemical formula. In 1 mole of CO2, I got 1 mole of carbon. And step three is STP. Just write that out. And then you can't screw this up as long as you're paying attention. Grams of carbon, moles carbon, grams carbon, moles CO2, mole CO2, to liter CO2 at STP. And yeah, it's a sample problem, but if all you did is this, you don't need Gary to show you how to do it. You're not really doing anything except this. This is the only new part. Okay. I don't need to see that. You don't need to draw this. But the order of these things is why this is such a well. And then at the end, if you went to 2 sig figs, you'd have 12.01. So 4 sig figs there, 3 sig figs there, but because that's 2, we have to round it to 2.27 liters. Now I can finish it, I can put all the signs in, put the numbers in, but you guys should be able to do that by now. So let's look at a practice problem or two. This has only one wheel, correct? It hasn't asked about hydrogen or sulfur in H2S. Dihydrogen monoxide gas is released from rotten eggs. This is such a pungent chemical that your nasal passages can detect it in parts per trillion, not parts per billion. That's how sensitive it is. It's a really annoying smell. Okay? It's also toxic. Not like rotten eggs will kill you, but this gas in any amount will. It's a dangerous gas. But that's only one wheel. Let's do 2. He's assuming you guys are idiots. He gives you all this. I'm not going to assume that. Fill in the missing entry. I'm going to change this. So, determine the mass of hydrogen. This is a D. Determine the mass of hydrogen in 1 liter of propane gas at STP. Given information about propane, you want hydrogen. So the wheel on the left is moles propane, the wheel on the right is moles hydrogen. And then just take it from there. So you what does he give you here? 1 liter, so 2 sig figs. I'm gonna wait till most of you have finished it, then we'll just compare answers. After this, we'll do number 3. STP, so 22.4 liters per mole, that allows you to go right to moles this. The formula allows you to go moles hydrogen, and 1 mole of propane, I got 8 moles of hydrogen. Periodic table gets you here, okay? And 2 sig figs in the answer. That is not hard arithmetic, you guys. Anybody? What you get? Yep,
0.36 grams hydrogen.
2 sig figs.
Oh,
How many sig figs did you give me?
0.362
0.36? What, grams?
grams.
Grams hydrogen. Everybody agree with that? It's not hard, it looks hard, kinda, but not really. Let's look at number 3. Again, you don't see STP. That makes sense, because ethylene glycol is a liquid. The formula for ethylene glycol, this is what you certainly don't need to know in your field. And it doesn't matter whether you put the OHs here, on this carbon, or here, or here, or here, on that carbon, as long as it's like that. So that's the common name for it. We'll learn in organic chemistry, if we do organic chemistry, that the actual chemical name is 1,2-ethane diol. The molar volume is this. So we don't need STP because he's given us liters per mole. How many hydrogen atoms are in 200 milliliters of ethylene glycol? Well, would you agree that we've got 2 chemical species here? So 2 wheels, right? Why don't you try that? You know you need 2 wheels. Whatever quantity you start with is the mole nut thing, the wheel on the left, and then take it from there. Notice that this is liters per mole, and he's asked you about milliliters. You could either represent this as milliliters per mole, and then leave it as milliliters, or leave this as liters and convert that to liters. Okay? You may find it easier just to do this. 55.9 milliliters per mole. Because 0.0559 liters is 55.9 milliliters. And then check your answer. And it should be to should be to 3 sig figs. And check your answer for it. Again, we could have converted it to liters, but if you leave it milliliters, you can stay here. I don't know if I really like the last couple pages in the section, but I'll tell you why in a minute. But first I wanna make sure you guys, is the process okay? And then when you check your answer, see if it's right. If it is, yay. Remember, this is just chemical formula, page 1 mole of ethylene glycol, I got 6 moles of hydrogen. 100 moles times that by 6.02 times 10 to the 23, you're gonna get a big number, all right? Now, if you left this as liters, then this is simply 0.2000 liters. Doesn't change your answer. And probably what Gary would have expected you to do is go milliliters to liters, liters to moles, moles ethylene glycol to moles hydrogen to average hydrogen. The answer that you get should be the same. No repeat. Bring in the horn. Who checked their answer? Nobody? Did you get it right? How many people got it right? Awesome. This is what you guys should do for homework. I've said it, I don't know how many hundreds of times. Find a question, do it, check your answer. Now, if there's a dramatic difference that isn't like a rounding or a sig figure, then that's what we should talk about. But if you don't check it, you don't know if you're doing it right, and you don't know if you're doing it wrong, which kind of negates the whole purpose of homework, all right? There's only one more thing in this section. And I don't know that we need to worry about the wheel thing at all, at all. Density is the amount of matter in a given volume of an object or material, mass per unit volume, you guys know that. If we hearken back, remember way back when I asked you, this is in September, and not just in September, but at the beginning of September. I said, why do we graph? Remember the answer we came up with? We're looking for a mathematical relationship between measured quantities. And the example I used was density. So if density is mass per unit volume, let's see, grams per milliliter. Obviously, if you got no volume of a substance, you got no mass. So for a solid or a liquid, density is constant, okay? Mass per unit volume. And we used water back then. And we said for water, 1.0 grams per milliliter. And then we use the graph, given any volume, you can get the mass, right? Given any mass, you can get the volume. Had we mentioned moles back then? No. So to overlay it on this is a little bit more than we need. Mass, the volume, the mass. Nothing to it. We already did that, but you don't need the wheel to do that. Given the y value, get the x. Given the x value, get the y. Using this, that's the slope of the line. Okay? So Gary tells us the density of methanol is this. What's the mass? I could have asked you that in the chapter 1 test. The density of methanol, a liquid, is 0.813 grams per milliliter. That's the slope of the line. And then he gives us a volume. 500 milliliters, 1.5 liters, doesn't matter. So 0.5 liters. What's the mass? Yeah. We could have done that in chapter 1. So I don't necessarily need to review that with you guys, do I? But what we can add legitimately here is if you know the density of the liquid or the density of any substance, it could be a solid, it could be a gas, if you know the density at a particular temperature and you know the formula, you can calculate the molar volume. And all you have to do is look at the units. Molar volume, if we agree it's liters per mole, everybody from a formula can calculate molar mass, right? So grams per mole. Density allows you to go to here. By doing that, okay? So that's just the inverse of the density. Multiply the molar mass by the inverse of the density, and you'll always get the molar volume. Now, with gases, the density is a lot more connected to the temperature. So, in other words, you would always be given the temperature if you're talking about density of a gas, but usually this is mostly indicated as solids or liquids, okay? Now, another way you could write it is molar volume equals molar mass divided by density. How does that work? Well, grams per mole divided by mass per unit volume equals this, okay? Invert and multiply. I like this better. Yeah. Yeah, go to the bathroom. So the new part of that is this, but the mass to volume and volume to mass isn't, okay? So the last page of this section in episode of whatever. Sulfur hexafluoride has a density of 6 grams per liter at room temperature and pressure, about 6 times that of air. What is the molar volume of sulfur hexafluoride under these conditions? Well, we know the density, we know the formulas, so we can get molar mass. So molar mass times the inverse of the density gives us molar volume, just like we did on the board, nothing to it. Now let's see which of these we require molar volume or are going to calculate. Does this question look familiar? Gold has a density of 19.42 grams per cubic centimeter. standard gold bar is held in, what's the volume of a standard gold bar, 12.4 kilograms? I either asked that exact question or something very similar to it on the very first test. There's no reference to moles. You don't need anything to do with moles here. This is just the graph. Mass and volume. Okay. Now, does he give you volume in cubic centimeters? Same here. It's a solid. So you're given mass in kilograms. Density is grams per cubic centimeter, so kilograms to grams. There's a slope of the line. Grams to cubic centimeters. You don't need moles, nothing. It's just 2 steps. And we did that back in September. Same thing here. Mercury has a density of 13.534 grams per milliliter. Not quite as dense as gold. What's the mass of that volume? It's milliliters because mercury is a liquid. So now we're starting from volume, going to mass. Again, no reference to moles. This one, though, you need it. Although ethanol is best known for type of alcohol, okay, whatever. I don't know if I agree with that, but the density of ethanol is 0.789 grams per milliliter. What's the molar volume? Well, you multiply the molar mass by the inverse of the density. The molar mass can easily be gotten from the formula. So this one does require this. You know the formula. C2H5OH. And again, why did they write it like that? Because there's the 2 carbons and the 5 hydrogens. And that makes it an alcohol. So that allows you to get molar mass multiplied by the inverse of the density. You've given it to milliliters, so you're going to get milliliters per mole. So most of that's just conversion gymnastics, okay? And that's section 3.4. Now students have asked me, more than one student has asked me, we're getting through chapter 3 pretty quickly. Does that mean we're going to have a test on chapter 3 before Christmas break? To which I answer, God, no. Okay? There's still lots of stuff in chapter 3. I don't want to rush through it. We haven't yet got to formula determination nor molarity. So no, we're not going to finish this in time for a test before Christmas. And I think it's probably unlikely that there will be a test immediately after Christmas. No one wants to come back after Christmas break, and the first thing they do when they sit down is, well, welcome back. I hope you had a good Christmas vacation. Here's your test. Plus, immediately upon our return, we have the voice chancellor treatment, right? So there's some goofy things there with scheduling. This is a pivotal chapter. The stuff in section 3.5 is brand new. The stuff in section 3.6 is brand new. And there's no point in rushing through it. We're even going to go a little beyond section 3.6. We're going to go temporarily into chapter 7 as well on solution chemistry. So we still got a lot to do. What I'd like you to do for next time, kind of what I asked you to do for today, pick a variety of questions in the 3-4 review questions, okay? And what did we do here? We talked about 2-step conversions, volume to moles to numbers, or volume to moles to grams, or back and forth. Then do some 3-step, where you pick 2 chemical species. And then maybe do some molar volume questions, where you gotta multiply molar mass by the inverse of the density. You don't have to do 4 or 5 of the same type of question. Do 1 or 2. And then if you get it right, you got it. You don't have to do them all. But try to focus on what's the different types of questions. And by doing that, then when you see them on a test, you go, yeah, I did that type. I know what to do. But if you don't practice, when you write your test, you're not gonna recognize what you're being asked, and plus, you'll learn for the first time that you actually don't know what you're doing, and you don't want that to happen in a test. Okay? When we got evaluated by these people from the ministry, whether or not I agree they were qualified to do what they did is irrelevant, but a big thing is self-assessment. They want to know that students are self-assessing themselves. And I said to the woman, and it seemed like a revelation to her, I said, that's the only reason I give homework. That's the point of homework, for students to self-assess. There's no other reason for it. And she said, do you give marks for it? I do. I said, I do, or they wouldn't do it at all. But the main point is for you to assess yourself. Do you know what you're doing, or don't you? That's it. That's homework. You don't get marks for homework in university, because no one cares. You get marks for tests. But what you do for homework is for your benefit, not for the profs. Obviously, if you do labs, if it's a science course, you'll have to do lab reports, sure. But in terms of the material, the content, knowing how to do it, that's on you. And that's why we put the answers that you have available to you to check your work. But if it's not going well, if you're not getting the right answers, then that's what we need to figure out in class. On rare occasions, the answer is incorrect, and we even see it in the Chem 12 books. But if you keep getting an answer that's different, then that problem has to be solved. And a lot of times the problem is tiny. I've said this to the parents in the interviews. If every time your son or daughter does a question and then they check their answer, if it's wrong, and the next time I see them, they ask me about it, sometimes it's a tiny little thing. It might be a subscript. It might be a decimal place. It might be a conversion factor that's flipped. But if you don't ask it, if you let it go, then little problems become big problems. And what we're doing here, remember how important chemical formula writing is. This is going to become more and more important, which means it's going to benefit you more, but if you can't do it, it's also going to cost you more. Yeah, and it is a rigorous course, I will grant you that. I would maybe suspect that I do more in one period than a lot of teachers do, but that's just because the course demands it. Okay? And there's nothing wrong with you getting a wrong answer. I expect that. I expect you to say, well, I tried this and this is what happened. What's wrong with it is if you get a wrong answer and you don't tell them. Or you just hope that it makes sense at some point in the future it won't. So the self-assessment is on you guys. You have to tell me what it is you don't understand. I do sometimes go through class and say, do this and check your answers, but we don't have time to do that every class. And that's kind of on you, okay? So for next time, pick a variety of questions in the 3-4 review. There's not that many of them because the variations on the theme in 3-4 are not that big. All we did is add volume. And check your answers and then we'll move on. So we're going to be starting something new on Wednesday. I don't see you guys till Wednesday, right? Because Monday's a Pro D day. Somebody thinks it's Pro D. I know what we're doing. I don't know that I agree with it being Pro D. I'd rather teach and slip my wrists actually.